Here is a brief overview of the new features to expect in JESD204D. PAM4 signaling is the new signaling, but NRZ is still there. Each will be running at 58 gigabaud, meaning 116 gigabits per second in PAM4 and 58 gigabits per second in NRZ, or what we would call also PAM2. The standard will heavily rely on the OIF CEI spec for the service requirements. And in PAM4, we will see the need for RS-FEC error correction. But in NRZ, we will only see the RS-FEC being used for error detection in place of the CRC mechanism. We will have Subclass 0, Subclass 1, and Subclass 3. And Subclass 3 will now be defined for systems using multi-ref instead of sysref for multi-point links. We will still have deterministic latency in Subclass 1 with the use of sysref, and the framing will be organized around FEC code words. Instead of sync header bits that we saw in 6466B encoding, there will now be a sync header burst used for boundary detection of FEC code words. And the data will be scrambled, and we will still have support for multiple converter devices aligned across multiple lane links, like before. And there's no changes in the transport layer, it will remain the same. Here on the right, you can see a picture that shows a payload that is being prepended by two symbols of the sync header burst and appended by the FEC parity bits. The big new thing for JESD204D will be the Reed-Solomon forward error correction encoding. It is required due to the high bit error rate on the PAM4 links, and depending on the link reach class, extreme short reach, medium reach, or long reach, different correction capabilities will be required. FEC1, FEC3, and FEC4 in the table here will be mandatory for the XSR, MR, LR classes, with FEC2 and FEC5 being optional. NRZ or PAM2 links will still use part of the FEC mechanism, but only for the error detection in place of the CRC mechanism from before. In the table, you can observe the different composition of the FEC modes. I will go into the details of these in a moment, but the key information to observe here is the overhead, which is in the mandatory classes 6.25%, and the correctable burst error length for each class. Now let's dive a little bit deeper into the world of Reed-Solomon forward error correction and how bytes become 10-bit FEC symbols, and how JESD204D will build FEC code words with sync header burst and parity symbols attached. A few new letters appear here that should be relevant in the standard. One of them is P, indicating how many payload bytes will make up a single FEC code word. This can be 160, 320, or 640 bytes. And assuming a single payload block is 160 bytes, we can say the FEC code word will carry 1, 2, or 4 payload blocks. In the image on the top right, we are demonstrating a single payload block inside of a FEC code word. So 160 bytes or 1280 bits will be represented as 128 10-bit symbols for FEC processing. These 10-bit symbols are the units of data that the FEC, RS-FEC uses, so we must do this conversion to understand the parameters. You can also see this when the FEC is defined, like RS-FEC 136, 130. The numbers here indicate the number of symbols in the FEC code word, 136, and the number of message symbols, 130. The message is 130 symbols because the RS-FEC also encodes the additional 2 symbols that are prepended to the payload as the sync header burst. I will explain the purpose of these 2 symbols in a moment, but just let's assume this happens. So 128 symbols in the payload becomes 130 symbols, 256 become 258, and 512 become 514 for the message. Now, FEC1, which is RS-136-130 in this example, appends 6 more parity symbols to form the FEC code word. And the FEC mechanism is able to correct half of these parity symbols, so 3. And we say it means it can correct up to a 21-bit burst, because that is the longest burst that spans 3 10-bit symbols if the bit burst starts on the last bit of the first symbol. This graphic should demonstrate how these FEC code words are put together in all different 5 FEC modes. For this demonstration, let's assume our frames consist of 8 octets, but they really don't have to. It just makes this image cleaner. But the important part here is that we take frame data and group it into payload blocks of 160 bytes. You can see these gray blocks here. And then the RS-FEC, when it's encoding this data, it works on symbols. So we can see the transition from 160 byte blocks, or a number of them, into the payloads in blue. These payloads will get prepended with the sync header burst of 2 symbols. And this sync header burst carries a constant bit pattern and an end of alignment block indication inside of it. And finally, this as a message gets passed to the RS-FEC encoder, and different lengths of FEC parity gets appended onto the end of the message to form the FEC code word, depending on which FEC mode is being used. These FEC code words are then sent across the serial link into the receiver, where the receiver will look for the pattern of the sync header burst to align to the FEC code word before passing the data to the FEC for processing. Now let's discuss lane alignment and how that might be handled. From JESD204C, we know we had a large framing structure called extended multi-block with the E parameter, and in JESD204B we had the multi-frame with the K parameter. And now in JESD204D there's a new parameter called A, and it will serve a similar function indicating how many 160 byte payload blocks will form a single alignment block. So this is our major framing structure, the alignment block. And A will take a value from 1 to 32, and the resulting alignment block must hold an integer number of frames. Since we'll be aligning on an alignment block boundary, it must be ensured that each alignment block starts with a whole frame. That way we always start deframing correctly. In the figure below, A is set to 2, and we can see in orange the sync header burst with the end of alignment block indication happening every second FEC code word, as each code word carries only a single payload block and the alignment block consists of 2 payload blocks. The blue arrows show where the alignment block boundaries are indicated by a sync header burst with the end of alignment block indication. So this is a simple example. And now let's move to a little bit more difficult one. It will not always be the case that the alignment block boundary coincides with a sync header burst. In this example, we set F to 12, meaning our frame consists of 12 octets, and frames no longer nicely align with each FEC code word payload. In this example, the FEC code word payload consists of 4 payload blocks, and we set our alignment block to contain 3 payload blocks. Containing 3 payload blocks allows it to align with a whole frame or start with a whole frame every time. But the FEC code word contains 4 payload blocks, and it will consist of the first one, where you can see the color change from orange to gray or yellow to gray. It actually, you can see maybe part of the frame is in one payload block and the other part is the next payload block, right? And again, the payloads will be RS-FEC encoded with sync header burst and parity symbols added. And on the bottom, we can see that not every alignment block will now fall on a FEC code word boundary and be covered with a sync header burst. So it cannot be indicated by an end of alignment block indication in that sync header burst. But those sync header bursts, the orange ones, will happen occasionally, right? And because we know A is equal to 3, we can imply the other boundaries that happen actually in the middle of the FEC code word payloads, as indicated by the gray arrows in this image. I will briefly touch on the topic of deterministic latency and the new subclass 3. This might seem familiar to those of you that have studied the JESD204C spec, as subclass 3 multi-ref mechanism already existed in the JSD specification. In JESD204D, however, it will receive its own designation of subclass 3. And we are skipping from 0 to 1 to 3 because subclass 2 already existed in JESD204B. It made use of a sync pin that no longer exists in these self-synchronizing receivers. So that's why there's this odd skip. In subclass 0, there is no deterministic latency and there is no way to align multiple converter devices data when they're separate devices. The data from the DSQ buffer is released as soon as all lanes provide the data in that specific device. In subclass 1, as before, sysref, that is in sync with the device clock, is distributed to all the components in the system, giving a precise timing reference allowing for deterministic latency. And in subclass 3, there is no deterministic latency, however, a multi-ref signal is shared across devices on a multi-point link, allowing them to have a common local reference used for aligning lanes on a common local alignment clock boundary, LAC.